Recursion is a technique used to solve bigger problems by breaking them into smaller, similar problems. The process in which a function calls itself directly or indirectly is called recursion. The corresponding function is called a recursive function. To some problems, recursion is very useful for developing efficient algorithms, and to others, it might add more complexity and overhead calculations with no improvement to efficiency. In the introduction lesson, we explained how recursion algorithms work and how they are implemented by a conditional statement. Remember, we said that you have to focus on two important points if you want to write a recursive algorithm. First is that in the recursive call, you have to supply a parameter different from the parameter received by the algorithm. The parameter must be updated when the algorithm is called recursively. Otherwise, the algorithm will never stop and will have a Stack Overflow error. As an example, if the input to the algorithm is n, as shown in this example, we may call the algorithm recursively with the parameter n-1, or you might update the parameter by n+1, or n multiplied by 2, or n divided by 2, and so on. Depends on the problem you are solving. And the second point to focus is to determine the stopping condition to stop the recursive calls. So in the if part of the conditional statement inside the body of the recursive algorithm, you specify the stopping condition, and the else part you do the recursion. Remember that all operations executed before the recursive call are called pre-work operations, and all operations executed after the recursive call are called post-work operations. Before showing you how to find the time complexity of a recursive algorithm, first we would like to talk briefly how problems are solved recursively and how the recursive algorithms are traced. We will also present a couple motivated examples as a review on how to write recursive algorithms. After that, we will focus on measuring time complexity of recursive algorithms. So let us start. Recursive algorithms solve a large problem by applying themselves to a part of the problem, and then using the solution of that part to solve the larger problem. So what do we mean by part of the problem? We mean in the recursive calls, the algorithm must supply data of size smaller than the size of the received data. Let me show you how by an example. Suppose you have an array of items with size n. We will show you two scenarios on how to make recursive calls with parts of this array with smaller sizes. In the first scenario, assume you have only the array as a parameter to the algorithm, as shown in this example. In this example, the algorithm is called solve with a single parameter that is an array called a starts from index 0 to index n-1, where n is the size of this array. Now how this is implemented in Java? In Java, if only the array is passed as a parameter to a method, then the size of the array is obtained by calling the length method. Now when you call the algorithm recursively to pass part of the array as a parameter, you need to pass it as a subarray. For example, in this recursive call, if you pass a subarray starting from index 0 to index n-2, then the input size is equal to n-1. And as another example, if you pass a subarray starting from index 0 to index n/2 minus 1, then the input size is half the size of the array, which is equal to n/2. And finally, in this recursive call, if you pass a subarray starting from index n/2 to index n-1, then the input size is also half the size of the array, which is equal to n/2. But passing subarrays in every recursive call consumes a lot of memory from the stack. And if there are a lot of recursive calls, then the algorithm might get an error that is a Stack Overflow and crashes the program. In the second scenario, the parameters of the algorithm are a reference to the array, followed by the start index of the subarray, followed by the end index of the subarray. In this case, when calling the method recursively, only the reference of the array and the subarray indices are pushed on the stack. That's why this scenario is considered more practical to implement than the previous scenario. But how the input size is computed from the subarray indices? It is computed by subtracting the start index from the end index plus 1. Now when you call the algorithm recursively, simply you write the name of the array followed by the subarray indices. For example, in this recursive call, if the start index of the subarray is 0 and the end index is n-2, then the input size is equal to n-1. And in this recursive call, if the start index of the subarray is n/2 and the end index is n-1, then the input size is equal to n/2. And finally, in this recursive call, if the start index of the subarray is 0 and the end index is n/3 minus 1, then the input size is equal to n/3. Our next discussion is what are the common cases in recursive algorithms for the definition of part of the problem. In some cases, that part of the problem may have only one less element than the full problem. And here is an example. In this algorithm, the parameter n is considered as the data for the algorithm as well as the size of the problem. As you can see in the recursive call, the size of the problem n is reduced by 1. These algorithms are called reduce or decrease and conquer algorithms. In other cases, the part of the problem may be half the elements in the full problem. And here is another example. Again, the parameter n is considered as the data for the algorithm as well as the problem size. As you can see in the recursive call, the size of the problem is divided by 2. These algorithms are called divide and conquer algorithms. Our next discussion on recursion is how to trace recursive algorithms. We will begin tracing an algorithm that has a single recursive call statement, followed by another algorithm with 2 recursive call statements. Here is an example of an algorithm with a single recursive call statement, where the name of the algorithm is P with a single parameter n. The algorithm has an if and else statement, and if n is equal to 0 at line 2, the algorithm stops and returns 1 at line 3. Otherwise, it prints the value of n at line 5, followed by calling the algorithm recursively with a parameter equals to n-1 at line 6. On returning from the recursive call at line 6, first the returned value is multiplied by 2, followed by assigning the result to the variable s, followed by printing and returning the value of s at line 7 and line 8 respectively. In our previous discussion, we've mentioned that any operation executed before recursion is considered a pre-work operation, and any operation executed after recursion is considered a post-work operation. The pre-work operations in this algorithm are comparing n to 0 at line 2, that takes us to the else statements, printing the value of n at line 5, and subtracting 1 from n at line 6. Subtracting 1 from n is considered a pre-work operation because it must be calculated before calling the method recursively. Now for the post-work operations, there are multiplication and assignment operations at line 6, and also printing and returning the value of s at line 7 and line 8 respectively. Now for tracing the algorithm, Let us call it from the main program and pass 3 as a parameter. After that, the return value from the algorithm, we want to store it into a variable that is called value. When the algorithm is called the first time in the main program with P3, passing 3 as a parameter, this parameter will be tested if it is equal to 0 or not at line 2. Since it is not equal to 0, then the algorithm will jump to the else statements starting from line 5. In the else statements, first the value of n, which is equal to 3, is printed on the screen, followed by calling the algorithm recursively by P2 with a parameter equals to 2. All operations in P3 starting from the multiplication operation until the end of the algorithm are suspended. They will be executed after returning back from the recursive call. Now we are inside P2. Since 2 is not equal to 0, then the algorithm will again jump to the print statement at line 5, printing the value of n, which is equal to 2, followed by calling the method recursively by P1 with the parameter equals to 1. Again, all operations in P2 are suspended, starting from the multiplication operation until the end of the algorithm, and they will be executed after returning back from the recursive call. Now we are inside P1. Since 1 is not equal to 0, then the algorithm will jump to the else statements and will print 1, followed by calling the algorithm recursively by P0 with a parameter equals to 0. Eventually, we are inside P0. Since n is equal to 0, then the algorithm will return back to the previous recursive call, returning 1 to the call P0. Now we are back inside P1. Multiply P0, which is equal to 1, by 2. The answer is 2. Save it into the variable s, printed on the screen, and return back to the previous recursive call, returning 2 to the call P1. We are now back inside P2. Multiply P1, which is equal to 2, by 2. The result is 4. Assign it to the variable s, printed on the screen, and return back to the previous recursive call, returning 4 to the call P2. Finally, when returning back to P3, multiply P2, which is equal to 4, by 2. The result is 8. Assign it to the variable s, printed on the screen, and return back to the previous recursive call, returning 8 to the call P3. That value is assigned to the variable value. So the final answer for P3 is equal to 8. So what is computed by the algorithm? To answer that, you need to observe what is calculated after returning back from the recursive call at line 6. Notice that in every recursive call, the return value is multiplied by 2. And since we have 3 recursive calls, then we have 3 multiplication by 2, which is equal to 2 to the power of 3, where 3 is the value of n. So the conclusion is that the algorithm is computing the value 2 to the power n, where n is the input parameter. As a final remark, notice that the trace of the algorithm formed a straight line moved in one direction in every recursive call, and returned back from recursion in reverse order in the opposite direction. Why? Because the algorithm has a single recursive call statement. However, if the algorithm has 2 or more recursive call statements, then the trace will not form a line. In fact, it will form a tree of recursive calls. That type of a trace will be demonstrated in the next example. This algorithm is exactly the same as the previous algorithm, except that instead of calling Pn-1 once and multiplying the result by 2, the algorithm is calling Pn-1 twice, as shown at line 5, where their return values are added and returned by the algorithm. This change will not affect the output of the algorithm. Still the algorithm is computing 2 to the power n, but it will affect its efficiency, where its efficiency will be deteriorated because there will be overlap of recursive calls and repetition of calculations. You will see that when we trace the algorithm. Just a quick remark. In the pseudocode, although the two calls at line 5 are combined in one statement, they are in fact executed as two separate recursive calls by the CPU. That's why we are considering this algorithm as an algorithm that has two recursive call statements. When the algorithm is called the first time in the main program with P3 passing 3 as a parameter, since 3 is not equal to 0, then the algorithm will jump to the else statement at line 5 and start calling itself twice with a parameter equals to 2. In this situation, the trace can be represented by a binary tree, where each internal vertex has a left child for the left call and a right child for the right call. The sequence of execution of these calls is that the call for the left child is first executed and the call for the right child is postponed, where it will be executed after returning back from the left call. In general, if the body of the algorithm has multiple recursive calls, then the trace can be represented by M-array tree, where each internal vertex has exactly m children of recursive calls. In our example, there are couple recursive calls. That's why we have 2 children of calls for each internal vertex in the tree. And if there are 3 recursive calls, then there are 3 children of calls for each internal vertex, and so on. Currently, P3 has 2 children. When P2, the left child, is executed, since the parameter 2 is not equal to 0, then it will call itself twice with a parameter equals to 1. The left call P1 is first executed, and the right call is postponed, where it will be executed after returning back from the left call. When P1, the left child of P2, is executed, since the parameter 1 is not equal to 0, then it will call itself with a parameter equals to 0. The left call P0 is first called, and the right call is postponed. Now on P0, since the parameter is equal to 0, then the algorithm has reached the stopping condition, where it will return back to its parent P1 with a value 1. Going back to P1, the right call P0 that was postponed will start executing, and also will return 1 to its parent P1. Now P1 has received the return values from both of its children calls. It will add them and return 2 to its parent P2. Now the algorithm is back to P2. It has finished calling the left call with a return of 2. And it is time to execute the right postponed call P1. In P1, P0 will be called twice. The left call is executed first and the right call is postponed. The left call will return 1 because n is equal to 0, and the right call will start executing and also will return 1 to its parent P1. P1 adds the 2 received ones and return 2 to its parent P2. Now P2 has received 2 from both of its children. It will add them and return 4 to its parent P3. The algorithm is back to P3, where it has finished executing the left call with a return value 4. Next is to execute the postponed right call P2. When this P2 is called, its left child P1 is executed first, and its right child is postponed. And when P1, the left child of P2, is called, its left child P0 will return 1, and its right child will also return 1. Now P1 will add the 2 return 1s and return 2 to its parent P2. Returning back to P2, its right child P1 is executed, followed by calling the left child P0, returning 1, followed by calling the right child B0, returning also 1. P1 will add the two return values and return 2 to its parent P2. Now P2 will add the two return values and return 4 to its parent P3. P3 will add the two return values and return 8 to the main program, where the main program will save it into the variable value. The question is, why the algorithm is inefficient? The answer is, there are overlap of calls leading to repetition of executions. Let me show you what I mean by this. In the beginning, P3 will call P2, and P2 will call P1, and P1 will call P0 and return 1. Now going back to P1, the algorithm needs to execute the right call P0. Executing the right call P0 is considered a repetition to the left call, because both return 1 to their parent, which is P1. In this case, we say that there is overlap between the two calls and their execution is repeated. Now going back to P2, the algorithm needs to execute the right call P1. But P1 will follow the same steps that the left call has already followed earlier. And again we have overlap of calls and repetition of execution. Now going back to P3, the algorithm needs to execute the right call P2. But P2 will follow the same steps that the left call has already followed earlier. And again we have overlap of calls and repetition of execution. As you see, the algorithm is executing the same algorithm over and over at every level of the tree, making the algorithm slow and inefficient. Later we will show you that the time complexity of such algorithms is in fact exponential. I mean equals to 2 to the power n. To continue the discussion on recursion, we will present two motivated examples, showing you how to think recursively to get a solution to a problem. The first example is finding the sum of the elements of an array. So we want to write a recursive method that finds the sum of the elements of an array that is called A. Its first element is at index 0 and the last element at index n-1, where n is the size of the array. To find a recursive solution, first you need to define the solution as a function with parameters that include the size of the problem, and then think on how to apply this function on part of the problem to get the solution to the whole problem. The function in our example is called sum, with two parameters, a reference to the array followed by the size of this array, where the function adds all the elements on the array starting from the first element A0 until the last element at index n-1. Now to think recursively, we can ask ourselves, if the function sum with the parameter n finds the sum of all elements of an array of size n, then what does it find if we replace n by n-1? The answer? It will find the sum of all elements of the array except the last element. In this case, we can say that the sum of an array of size n can be found from the sum of its elements for a size of n-1 plus the last element. Let me explain that by an example. In this example, the size of the array is 4, and we want to use the function sum to add the elements of the array. When we call the function the first time with size 4, the function is required to add the elements a0 plus a1 plus a2 up to a3. So, sum of a with size 4 is required to add the elements a0 plus a1 plus a2 And finally, the last element is A3. Now, if the function with size 4 adds the elements from A0 to A3 and it gives this formula, then the same function with size 3 adds also the elements from A0 up to A2 and also gives this formula. So therefore, we can say that this formula, which is adding the elements from A0 up to A2, can be replaced by the result that is obtained from calling the function sum with size 3. So here we say that sum of A of size 4 is equal to sum of A of size 3 plus the last element, which is A3. Similarly, when we call the function sum with size 3, we can call the same function sum with size 2, adding the last element for a size of 3, which is at index 2. Similarly, when we call the function sum with size 2, this is equal to sum of size 1 plus the last element, which is at index 1, when we call the function with size 2. Finally, for sum of size 1, we have only one element in this array. So this function, when it is called with size 1, it retains the only element which is at index 0. And this will be considered as the stopping condition. So now we can generalize the recursive call of this function with a size n. And here we say that when we call the function sum of A with size n, we can make it equal to sum of A of size n minus 1 plus the last element of size n, which is at index n minus 1. And for the stopping condition, when n is equal to 1, the function will retain the value of A0. From the example, we conclude that the sum of A of size n is equal to sum of A of size n minus 1 plus the last element that is at index n minus 1. And for the stopping condition, the algorithm will stop when n reaches 1. That means we have only one element in the array, so the algorithm retains that element that is at index 0. The implementation of the algorithm first is the stopping condition. When the value of n is equal to 1, we have only a single element of the array. The algorithm retains 0. Otherwise, the algorithm calls itself recursively by calling itself with a size of n minus 1 plus the last element that is at index n minus 1. For our next motivated example, we want to write a recursive algorithm that returns the number of digits of an integer. To use recursion in the solution, first we need to define the function that will provide the solution and what are its input parameters. In our example, the function is called len, that stands for length, and has a single parameter n, that is the number we want to find. How many digits does it have? Notice that the parameter n is the data to the algorithm as well as the input size. So the question is, how to apply this function on part of the number to get the solution for the whole number? Let us take an example to show you how to do that. Suppose n is equal to the number 2, 0, 4, 0, 5, 0, 7, and 3 with 8 digits. Then the function returns 8. Now when we call the function on the number itself, but without the rightmost digit, that is a 3, then what the function will return? It will simply return 7 because it has 7 digits without the rightmost digit. Notice that the number without the rightmost digit is obtained by dividing the number by 10, I mean integer division. So we can find the length of the number by finding the number of digits of itself without the rightmost digit, that is a 3, and it will be equal to 7, plus 1 for the rightmost digit. And this can be generalized by saying the length of an integer of size n is equal to the length when it is divided by 10, deleting the rightmost digit, plus 1 for the rightmost digit. And the stopping condition is when n reaches 0. But we cannot implement the stopping condition by saying if n is equal to 0, return 0, because when the function is called the first time with n equals to 0, the number of digits is not 0, it is equal to 1. Therefore, to solve this issue, we will check for the stopping condition. If n has a single digit, the algorithm returns 1. And this can be implemented by testing if n is less than 10. So if n in the beginning is equal to 0, it is less than 10, the algorithm returns 1, that is a single digit. Otherwise, after multiple division by 10 recursively, the number will become single digit and it is less than 10, the algorithm also returns 1.